Welcome back to Finite Element Methods. So class number 16, where we're talking about the condition number of the stiffness matrix. Now, this is the stiffness matrix for the standard model problem, the symmetric model problem. And we could look at the stiffness matrix also for the non-symmetric problem as well. That would be a little more difficult, but the ideas are basically kind of similar. So recall that the model problem has a bilinear form, which looks something like this, right? It's, of course, the model problem is in strong form minus Laplacian u equals f and u equals 0 on the boundary. So just to remind you, that's the problem we're talking about. Of course, to get the weak formulation, we multiply by a test function, integrate by parts, and then the Galerkin approximation follows pretty quickly from that. So if you consider the Galerkin approximation for the model problem, it's written as follows. We're going to look for a function from a finite dimensional space, which turns out to be a Hilbert space in this case. And the particular one we're going to be interested in are going to be these piecewise polynomial spaces where if I restrict to a triangle, we're going to get a degree R polynomial. So piecewise polynomials of degree R. The zero means that we are enforcing zero boundary conditions for the problem, even in our Galerkin finite element approximation. What makes this a finite element is that we're taking the particular finite dimensional space to be a piecewise polynomial space. And that's what makes it finite element. If we choose something different, then we'll get another method out of it. You may have heard of something called the spectral Galerkin before, and that's another type of Galerkin method where instead of using piecewise polynomial spaces, we use sines and cosines essentially. In any case, we're looking for a solution from our finite dimensional space, our piecewise polynomial space that satisfies this version of the weak problem. We call this the Galerkin problem. And the test functions in this case are all v in the subspace VH. As I said, we have a very particular bilinear form for the model problem, and that is AUV is equal to the gradient of U dotted with the gradient of V in the L2 inner product. Of course, I can rewrite that as the sum over all derivatives of exactly order 1, partial U times partial V, alpha partial derivative of U times alpha partial derivative of V in the L2 norm. And of course, I've got a sum over those. So what is the stiffness matrix? Let's recall what we mean by stiffness matrix. Well, it's a square matrix having nr0 rows and nr0 columns. From now on, I'm just going to say n, even though I'm writing the full nr0. You recall what that means. And the components of this matrix are what we call aij. So the component in the ith row and the jth column is what we call aij. Of course, what this means, this number is just the dimension of our space, our finite element space. It's finite dimensional. That's the piecewise polynomial space of degree R. So we talked about what the dimensions of those spaces are at least in 2D and 1D. And the components of the stiffness matrix Aij are equal to A phi j phi I, where phi j and phi I are basis functions. And these are like the hat basis functions that we discussed in class. I guess we could say here for I and j between 1 and n. Right? So this was our standard basis. This is what we call the Lagrange nodal basis. So hope that rings a bell. Right. So that gives us a square matrix. It also is clear because this bilinear form is symmetric that I can interchange these entries. And so this immediately gives me the symmetry of the bilinear or of the matrix because aij equals aji. So here's what we're going to prove. So let's see. Suppose that tau h is a quasi-uniform shape-regular family of triangulations of the 2D polygonal domain omega. So I've introduced already what we mean by a shape-regular family, but I've never talked about quasi-uniform. Let me give you the definition for that. So what I mean by quasi-uniform is there are and shape regular. We'll do quasi-uniform first and shape regular second. There are constants beta 1 and beta 2, both greater than 0, both of them independent of h, such that h over, sorry, hk over h is greater than beta 1 for all triangles in the mesh, or all triangles in the triangulation, and for every h in our parameterization family. So usually what's happening is h is getting smaller and smaller, and we think about that as parameterizing the mesh. Now, h, what was h? Let's recall that h was equal to the maximum taken over all triangles in the mesh of hk. And hk was, of course, the diameter of the triangle, the longest, basically the measure of the longest edge. So this this ratio, let's think about this for a minute. What is this ratio saying, or what do we know about this ratio? Well, already we know that h, because it's the maximum over all the hk's, is bigger than any of the hk's, bigger than or equal to any of the hk's. And so this ratio always has to fit under 1. That ratio is less than or equal to 1. It's always going to be positive as well. Now, what else do we know about this guy? Well, nothing else. So we've got to make some assumptions about it. And the assumption of quasi-uniformity is the assumption that this ratio never degenerates as as h goes to 0, as h gets smaller and smaller. Now, what this means is that basically another way I could put it is if I take the ratio of the minimum h, where h min means take the min over all triangles in the mesh, and then look at h min over h. Of course, h is h max, really. And this is saying that my largest and the smallest triangles in the mesh are not too far off. Okay. The ratio is some number which is less than 1, but always bounded away from 0. Now, it could happen if you're not careful and you don't have what's called quasi-uniformity. You could have a mesh where this gets really, really small at each level of the mesh. So this could deteriorate as you get finer and finer grids. This could deteriorate to 0 a lot faster than that measurement could. And so in that case, what we would say is that we don't have a quasi-uniform mesh. Quasi-uniformity means that this ratio is always going to be bounded below by some constant. What it's saying is it basically means that the h min and the h max on every level of the mesh is roughly the same. They don't diverge from each other. The h min and the h max. That's roughly what that's saying. Well, in fact, the ratio of h min over h max not decaying to 0 is essentially equivalent to that. All right, so that's the idea of what's called quasi-uniformity. It basically means the mesh is what we call quasi-uniform in the sense that the measure of the sizes of each triangle aren't very far off from each other. They always maintain some sort of positive ratio. And of course, shape regularity is something that we've seen before. Um, that involves the ratio of rho k over hk. Remember, rho k is the diameter of the largest inscribed circle. So rho k was computed by fitting a circle in a triangle. Let's see if I can fit that in there nicely. Yeah, roughly speaking. Okay, so now to get rho k, all I do is take the diameter of this guy. So that's what we call rho k. And hk, of course, is going to be that measurement. We know that hk is always going to be strictly bigger than rho k. So this ratio is always going to fit strictly under 1. But if it doesn't deteriorate as you make more and more refinements of the mesh, then we say that that mesh is shape regular. So what shape regularity means is the 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 triangles don't become needle-like. The triangles don't become needle-like. In other words, we don't ever get triangles which look like this. That's more and more of a needle-like triangle. Roughly, it's saying that the triangles always stay basically like an equilateral triangle. It's not exactly right, but it's roughly right. Okay, so those are the two assumptions that we're making about the mesh. What we're going to prove is that there exist two constants, C1 and C2, where C2 is going to have to be bigger than C1, such that the condition number of A has the lower bound C1 H minus 2 power, and the upper bound C2 H to the minus, that should also be minus 2 power. So, okay, so it's sandwiched between these two parabolic, well, they would be parabolic, so inverse parabolic curves. What is this saying? Um, well, I should probably say that, first of all, C1 and C2, I thought I did say that, um, are independent of H. Um, yeah, I'll add, let's see, we can add it now. Just have to do a little bit of surgery here. Independent of H. That means they don't get smaller or larger as H is changing. Remember, H's are constantly changing mesh spacing. And think about it like this. We refine the mesh and the mesh spacing gets smaller and smaller and smaller and smaller. Otherwise, you're not really doing anything interesting. The mesh spacing should be getting smaller. But as we get mesh spacing smaller, what this is saying is that this condition number is pinned between two inverse quadratics in H. So H gets small. What happens to H to the minus 2 power? It gets large, right? So as H gets small, H to the minus 2 power blows up. Um, Now, we're caught between two curves which blow up as H gets smaller and smaller that are of roughly asymptotically the same shape. So what we say in this case is that K, or kappa 2, that's the two condition number of A, blows up like H to the minus 2 power. So that's the notation that we use. This says that the condition number is getting more and more ill-conditioned as H gets smaller and smaller because this number is getting bigger and bigger, and so is this guy. But by the same rate. The rates are the how fast is going to infinity as H is getting smaller. Okay, so this is saying something bad about the condition number. The condition number, we would like for that to be of order 1. Uh, you know, uh, 10 would be fine, 100, that's fine, but we don't want it to be the size of a million. And the reason why is because numerical methods start to suffer for when you're dealing with matrices which have very large condition numbers. So we talked about this in 571 and a little bit in 572. We also talked about this quite a bit in the courses on multigrid that I taught last semester in the last year, last academic year. We taught about how we talked about how you can overcome this ill conditioning to still get good solutions and reliable solution strategies for solving your your linear equations. So on one hand, we can say that there's something pretty good about A. A is symmetric. It's also positive definite. So we, of course, call that a symmetric positive definite matrix. But on the other hand, this condition number estimate is showing that the condition number is blowing up as H is getting small. And that's the crucial idea. We're going to usually take H to be smaller and smaller, and so we don't want this to happen. Unfortunately, we don't have any control over it. Now, I'm only going to focus in this proof on proving the upper bound because the lower bound is a lot more tricky and involves a lot of extra machinery that I don't have. So I'm simply going to point you to where this lower bound can be proved. So if you're interested in seeing how the lower bound is proved, you can see the book by Dietrich Bress from 2007, and that's where that's covered. So let's focus on this upper bound. How do we get that? Well, we know that A is SPD, and the condition number of any matrix is defined like this. I hope that you remember that from your numerical analysis course. For an SPD matrix, and for the fact that we're using the spectral norm, the condition number comes out very simply to be lambda max over lambda min, the maximum eigenvalue of A over the minimum eigenvalue of A. Now, unlike the case of, like, say, finite difference methods, we can't really say what lambda max and lambda min are exactly. We have to estimate them. And this trick, this analysis is what is going to be, this analysis that you're about to see is what we used essentially find out how big the biggest eigenvalue is and how small the smallest eigenvalue is. That's essentially it. Well, so let's let V be any function in VH, or finite dimensional subspace. Let me make that more clearly in H. Then there exists V1 through Vn, real numbers, such that V is equal to this linear combination through these basis elements phi I. In this case, we call V1 through Vn the coordinates of V with respect to the basis B. And oftentimes I like to write it like this. We have a V in VH connected to the vector of coordinates V, and this vector coordinates, I guess I should have written it. Uh, I meant to write that V is the vector of the coordinates V1 through VNR0. Okay. So this just says that any V in VH can be thought of as its coordinate vector through the basis. And conversely, if I think about a coordinate vector through the basis, I can reconstruct any finite element function in VH. Okay, so this link provides a one-to-one mapping between this space and that space. And of course, you can see right away that they have the same dimensions. Now, from a homework problem, you're going to actually prove that there exist constants, C3 and C4, which are independent of H, such that if I'm interested in the L2 norm of V squared, Okay, so this is a function in my finite element space. I want to take the L2 norm of that. Of course, that's just an integral. I can break that into an integral over separate triangles. I can show that this norm squared, this L2 norm squared, is less than a constant times h squared times the Euclidean norm squared of its coordinate vector. And I can find a similar lower bound, C3 h squared, the Euclidean norm of the coordinate vector squared. This object here, and of course this scaling and that scaling are exactly the same. What's different is these two constants, C3 and C4. What we know from that homework problem is what you can show is that these constants C3 and C4 are independent of H. And you can use this trick called the reference triangle scaling trick to prove this inequality. All you do is basically you start with, on the reference triangle, you make the argument that uh, that the L2 inner product, and again, we're on the reference triangle, of a function on the reference triangle is equivalent to, or the norm of that is equivalent to its Euclidean norm of its coordinates. And then you use the scaling argument the same way we did when we were proving the uh, error estimates for interpolation. All right, so that's one thing to put in your pocket. Now we're going to use another fact that we proved in homework. This is what's called an inverse inequality. An inverse inequality. So there exists a C5, again, independent of H, such that for any V and VH, you have to be in the finite element, finite dimensional space, VH, for this to work. We can show that AVV, which is another way of saying V's H1 seminorm, is less than a constant times h to the minus 2 power times the L2 norm of V. So this also can be done using a scaling argument and the reference triangle. Now this cannot hold, it can't possibly hold for any V arbitrarily from the infinite dimensional space H01. It can only hold for the subspace of functions from the finite element space. So it has to be from the finite dimensional space. If you were to ask me whether it's true for any V in H01, the answer is emphatically no. It doesn't work for that big infinite dimensional space, but it does work for the finite dimensional space. Now, what you have here is, we call this a weightier norm because it involves derivatives of the function v. All right, this is kind of like the reverse of what you would try to prove with a Poincare inequality. To get this reverse of the Poincare inequality, well, we can get something close, but we have to pay a price. And the price that we have to pay is that you get this scaling factor of h squared, which gets worse and worse as h gets smaller and smaller. Again, h minus 2 goes to infinity as h goes to 0. So it's a little bit like being able to prove a reverse Poincare inequality, but not with a constant, but with a constant times a scaling with respect to h, which scales kind of badly. And that's because we're trying to do something which can't normally be done in infinite dimensions. It can be done in finite dimensions, but I've got to pay this price. All right. Now, with those two estimates, 16.3 and 16.4 in your pocket, so this one is called the inverse inequality. And this one here, I don't have a name for it. It's equivalent equivalence of norms of the function and its coordinate vector. And that's about the best way I can put it, or almost equivalence, I should say. And then on the other hand, we're talking about an inverse inequality. So those are the two things we need to prove this result. We're going to use what's called the Rayleigh quotient. So the Rayleigh quotient for a symmetric positive definite matrix A is a well-defined object. And well, I suppose it's well-defined if A is even just a symmetric object. But A is symmetric positive definite, and the Rayleigh quotient for A is a function of vectors V. We can think about these vectors as being a bunch of different possible coordinate vectors for our finite element functions. And the way you compute this guy is you multiply first A times V, you take that result and you're going to dot it with V again, and you divide that by V dot V, or in other words, V transpose V. It's not hard to show that these two objects, V transpose A, V, is linked to A, V, V, where V is, let's write it here, V is that function in VH, which is connected through the basis B to the coordinate vector V in R in R0. Okay? And this is just the coordinates of this vector. Okay, so keep in mind every time I write V vector, I can also think about, as long as it's in this vector space, R and R0, a companion V in the finite element space, and vice versa. I can go back and forth. These two spaces are identified. So we showed a long time ago that these two things are exactly equal. And when did we show that? We showed that when we were first proving that A is a positive definite matrix. All right, now let's use 16.4, that's the inverse inequality, to estimate this guy on the on the on the upper side, or the upper given upper bound to this object here. Well, the upper bound that we have from 16.4 is C5 h to the minus 2 and V's the L2 norm of V squared. Now we're still dividing by its Euclidean coordinate vector norm squared. And so these two objects aren't exactly the same. This one is a norm of its coordinates, and this is the norm of the function. But we have this inequality here, which relates the two. So let's use this part of 16.3. So that says that this number here is less than C4 h squared Euclidean norm of V coordinate vector squared. Now I can cancel these two things, right? I can also cancel the h minus 2 and the h to the 2 power. So all I'm left with is then C4 and C5. And of course, that is definitely a constant. Now, that's the upper bound for the Rayleigh quotient. Let's go for a lower bound of the Rayleigh quotient. All right, lower bound for the Rayleigh quotient. Well, the Rayleigh quotient is still defined in exactly the same way. We still can show that V transpose AV is equal to AVV. And of course, by this V, I mean the V in VH is gotten as the identified vector, or well, identified function from the finite element space that has the coordinate vector V in, nope, R and R0. Okay, so they're connected to each other. So I can show that these two objects are exactly equal. Now I'm going to bound this guy from below, and we're going to use the basic Poincare inequality to do that. So the Poincare inequality says that the H1 seminorm squared is greater than some constant times the L2 norm of the function V L2 norm squared. And this holds for any function, not just in the finite element space, but in H01. Okay, anything in H01, it works. So that's Poincare inequality. Now again, this guy and this guy are not the same objects, right? One is a finite element function, one is this coordinate vector in R and R. But I'm going to use 16.3 again. I just need to use what? Let's use the lower bound on that guy. The lower bound says that the L2 norm squared is greater than C3 H squared coordinate vector V, that norm, right? So I'm bounding this guy from below, and that gives me a C3 H squared Euclidean norm of the coordinate vector squared. Again, those two objects cancel, and I just get something, some constant. Now, these constants are independent of H, definitely. This one's definitely independent of H, but I said C, C4, C5, they're all independent of H, and C3 is independent of H, and CP is independent of H. Now, the largest, you probably know this or have heard this, the largest possible value of the Rayleigh quotient is obtained by putting in the eigenvector associated with the largest eigenvalue. And the largest value that it takes is lambda max. That's the largest that the Rayleigh quotient could possibly be. And our estimate said that, well, for any vector, we have this upper limit, and therefore that holds true for the eigenvector as well. So this gives an upper bound on lambda max. The smallest value that the Rayleigh quotient can be is given by inputting the vector eigenvector associated with the minimum eigenvalue. This, of course, is a positive number, and so is that one, because a symmetric positive definite matrix always has positive eigenvalues. But now I have a lower bound on the Rayleigh quotient for any vector, and that's C3 CP H squared. So let's put this together. The condition number of A is the quotient lambda max over lambda min. So this one I can directly use the upper limit C4, C5. But this guy, what I'm going to do is I'm going to take a reciprocal. So I can show that if I have a lower bound on lambda min, then I have an upper bound on the reciprocal of lambda min of this type, CP H squared, 1 over that, right? And so now I'm just using the fact that I have an upper bound for this and 1 over lambda min. That's a product, right? This quotient can be thought of as the product lambda max times 1 over lambda min, and I have upper bounds on both of those. Well, since I do, I can combine them to get this upper bound for both. The product has that upper bound. C4 over C5, C4 times C5 over C3 times CP. This whole constant is independent of H. And where did the H to the minus 2 power come from? Well, it's because I have an H squared there in the denominator. I'm just bringing it up into the numerator. When it comes up into the numerator, its exponent changes sign. So that's it. That's the upper bound that I wanted to prove, that kappa 2a, the condition number, the spectral condition number of the stiffness matrix is less than some constant which is independent of H times H to the minus 2 power. Like I said, the lower bound is much harder to prove. It requires a lot more theory than what we want to go into, but that can be found in the reference that I shared earlier. It can also be found in the multigrid book that we wrote, and some of you have a copy of that. So I've already said this, but the condition number is getting bad as H is getting smaller and smaller. And so we say that this stiffness matrix A is ill conditioned. Its condition number is growing worse as one of the parameters in the system, one of the important parameters in the system, is getting small. And that's, of course, that's usually what we're interested in. So now there are two bad things associated with the stiffness matrix as H gets smaller. So as h gets smaller, the number of rows and columns of A gets larger and larger, and the number of degrees of freedom in the system gets larger. So I'm already having to deal with the fact that my degrees of freedom are getting bigger. Simultaneous to that, I'm having to deal with the problem that the stiffness matrix is becoming more and more ill-conditioned. So these are two big problems that I have to fight at once. But the good news is there are a lot of methods for dealing with problems like this, ill-conditioned problems. One of which is the multi-grid method that I talked about extensively last year in a two-semester course on multi-grid methods. And there's a book coming out with the same title, Multi-Grid Methods, which has all that theory in there if you're interested. So now we want to switch gears a little bit. We've been talking exclusively about second order partial differential equations, the model problem and that weird non-symmetric problem. That's the only two problems we've really solved or kind of solved in this course so far. And we haven't really solved them, I suppose, because all I've told you is how how well the finite element approximation works in some sort of convergence sense. We haven't really talked about computation, and computations are hard. Um, and we haven't talked about uh, what complicated domains or boundaries or anything like that. So, you know, one of the things I want to emphasize when we're talking about finite element method is um, it looks like you're putting in a lot of work and getting out only a very little. But the good news is that those two problems that we solve cover quite a lot of area. And even though we're not talking about problems on complicated domains, we've only talked about polygonal domains, and we only really hit on one and two dimensional things. Three dimensions is a little bit more complicated. We haven't even really talked about that. But these two-dimensional problems that are covered by these finite element methods cover a lot of applications. So even though it seems like we haven't really solved, we've only solved two problems, right? We've actually covered quite a lot of area. But now we want to expand what we're talking about to see if we can, so the kind of a lot of the rest of this course are talking about partial differential equations and applications of finite element methods to them that don't fit this model of second order linear. They're a lot more challenging in some ways. So here's our first challenging problem, which is not a second order problem. It's called the biharmonic problem. And it's given as follows. We suppose that f is some continuous function over the set omega. We're looking for a u, which is a C4 function intersected with C1 omega over line, or the C1 on the set closure of omega, such that, and we'll see why we need C1 in just a second, such that the Laplacian of the Laplacian of u, we're going to call that Laplacian squared u, such that the Laplacian of the Laplacian of u is equal to f. So this is like four derivatives. In one dimensions, it's a lot easier. It's just just purely four derivatives of u. In two dimensions, it's a little bit weird because the Laplacian of the Laplacian is it involve weird mixed partial derivatives of fourth order. Um, right. So what are the boundary conditions for this problem? Well, the boundary conditions that we're going to use are what we call clamped type boundary condition. Clamped type boundary conditions. The first one is we need the big difference between this and the second order problems is we need two boundary conditions simultaneously on the boundary. The first one is homogeneous Dirichlet, and the second one is homogeneous Neumann. The normal derivative of u equals zero on the on the boundary. This is what we usually mean by normal derivative, right? So that's n dotted with the gradient of u. That's how we define that object. And of course, this is the outward pointing unit normal on that boundary, as usual. As I said, the boundary conditions are called clamped type boundary conditions. Now, what space should we use to solve this problem? Well, we can't use and then the bigger question is on what space should we pose a weak formulation for this problem? That's a good question. That's not exactly clear right away. So rather than try to deduce what should work, let me tell you what does work, and then we'll kind of agree that that's probably the only thing that could work. Here's the space that I'm going to use. I'm going to use a space called H02. It's some subspace of H2. And by H2, we remember what that means. It means H2 is the set is the Sobolev space of all functions that are twice weakly differentiable and whose all of whose partial derivatives up to and including the second order are L2 functions. Those partial derivatives uh, are weak derivatives or understood as weak derivatives. They exist and they're L2 functions. So what is this space? So this space can be thought of in various ways. It's a subspace of H2 such that V and the normal derivative of V are 0 on the boundary. So this space is a Hilbert space. It's a topologically closed proper subspace of H2, and this space can be thought of as, you can prove that it is the closure of this space, C0 infinity. This is the space of compactly supported C infinity functions on the open set omega with respect to the H2 norm. So this is the closure of this space under that norm. Okay? That's how you get that space. You can also define it this way and it will make sense. But proving that these are actually equal takes a bit of analysis. Now, let's take a test function from that space. We're going to multiply this equation by a test function, and we're going to integrate. And we're going to use something called Green's second identity. In other words, Green's second identity says, let me put L2 inner products here. Actually, let me say more than that. There are L2 inner products over the whole of omega. And I'm going to distinguish between those and L2 inner products on the boundary, as usual. Okay, so this is what Green's second identity says. So when you get off this Zoom, go look this up, or you can even do it now. Google it or use your favorite AI to look up this identity. This is called Green's second identity. Now, what I'm going to do is rather than use W here, I'm going to replace W with Laplacian of U. That gives me the fourth derivative, or um, the Laplacian squared um, of U, just Laplacian of U here, and then some boundary terms, right? If I replace W by Laplacian of U. But remember, V is coming from the test space H02. That means V and its first partial derivative, its normal derivative, are 0 on the boundary. So these boundary integrals go away. So that says that this second partial, or the second Laplacian squared of U, integrated against V in the L2 inner product, is equal to the Laplacian of u times the Laplacian of v in L2 inner product. So in other words, what we get is when we multiply by that test function and use Green's second identity, we get down to this weak form. So if u really does solve this problem up here, then it's pretty easy to see that Laplacian of u uh, integrated against Laplacian of v, again, this is the L2 inner product, and that's L2 inner product, is equal to f of v for all v in that test function space. Okay, so this is what we're going to use as our weak formulation for the biharmonic problem with clamp boundary conditions. So that's my next definition. What is the weak formulation of the biharmonic problem with clamped boundary conditions? Well, it's defined as follows. Given any f in L2, why f in L2? Because we don't need f to be a continuous function anymore. It can be something as rough as an L2 function. We're looking for a u in v equals to h0, 2. So in other words, we're going to make the test function space and the solution space equivalent. And this is the usual thing in the Galerkin finite element method, or the standard weak formulation of an elliptic boundary value problem. We make the solution space equal to the test function space. So we're looking for u in H02 such that AUV equals FV L2 inner product, where this is now what we're going to call the bilinear form AUV, and it's just Laplacian of u integrated against Laplacian of v over the whole domain omega, right? So this is our new bilinear form for the biharmonic problem. Now, that's the weak formulation. And if we have a solution to that problem, that's called the weak solution to the biharmonic problem, okay? And it's easy to get a Galerkin approximation in this setting as well. So how do we do Galerkin approximations? Same deal, same way. We're going to let VH be some finite dimensional subspace of V. We don't know how to make a finite dimensional subspace yet, but let's just suppose one does exist. If a finite dimensional subspace of H02 exists, we'll set that to be VH. Right now, we don't care what it is. The Galerkin approximation of the biharmonic problem is defined as usual. We're going to look for a UH in VH such that this weak form problem holds, right? AUH against V, same bilinear form, and the right-hand side, missing an L2 there. L2 inner product of F against V for all V and VH. That's how we define the Galerkin approximation. And from this, of course, we know how to define the stiffness matrix for this problem, as long as we can figure out what a basis for this that space should be. And usually we're going to try to use something like a Lagrange nodal basis if possible. Okay, but it doesn't matter because we know that every finite dimensional subspace has a basis, and whatever it is, it can be found, right? Okay, so I need a couple of things, and most of these facts that we need, I'm going to relegate to a coming homework exercise. So on Thursday, I'll post another homework, and these problems will be in there. Now they turn out they're not too hard, so that's the good news. So what is the first one? The first one is like a Poincare inequality. It's a Poincare-like inequality for the for this setting. Okay, so let omega be a bounded and open set in RD. There exists a constant c greater than 0 such that for all v in H02, the H2 seminorm of u squared is less than some constant times the L2 inner product of Laplacian U against Laplacian U. And that's the same as the L2 norm of Laplacian U squared. Okay, this object. So this is bounded above by that object. So this is a Poincare type or like inequality. So let's write that. So I'm going to leave it to a homework exercise for you guys to prove this, or some simple version of it. Maybe you could prove this on a square, for example. All right, but this holds true for any bounded and open set. That's nice. Um, right. So uh, the next thing we want to know is that bilinear form that we created coercive and continuous on our space of interest with respect to, let's say, the only norm we know about on that space is going to be the H2 norm right now. And the answer is yes, it's both coercive and continuous. The coercivity is actually proved from this theorem right here. What about continuity? Continuity is actually easy. You just apply Cauchy-Schwarz inequality. So this homework exercise is nothing more than taking the last result, or the result from the last theorem, and using Cauchy-Schwarz inequality, put those two things together and you get coercivity. Coercivity comes from that, and continuity comes from Cauchy-Schwarz. So it's actually an easy one. Okay, so bilinear form is coercive and continuous. As a corollary, this bilinear form here, which is the A bilinear form, let's say it like that, A, but it has a special name attached to it. Oops. We call it we're, we're going to give it a symbol which makes it seem like it's going to be an inner product because it is an inner product. Okay, so this was our bilinear form that we defined above. And what this little corollary says that because of this last result, you can even use this result, we can show that this bilinear form, which we're going to define that way, is actually an inner product on H02. It's not an inner product on the whole space H2, only an inner product on H02. Remember, this is the subspace which has the function and uh, its normal derivative being 0 on the boundary. Now, if I pair that inner product with this space, then this becomes a Hilbert space. It's a closed, topologically closed subspace, proper subspace of H0, or sorry, of H2, and therefore it's a Hilbert space. And the norm, how do I get a norm? Well, I just take that inner product object and I put U in both locations, the first and second slot, take the square root, and that defines a norm. Okay? If this truly is an inner product, which it is. Now, but it is interesting that this norm that I just created is not equivalent to the H2 semi-norm. Now, that was different than in the world of H1, where this norm that we defined was the H1 semi-norm. But here for H2, it's not. This is still true. But these two norms this one I just defined, this one, I hope that you remember how it's defined. They're not equivalent. So that's a little homework exercise to see that. It's actually a very quick one. Now, since we know that the bilinear form is coercive and continuous, then both the weak formulation of the biharmonic problem and its Galerkin approximation problem have unique solutions. So both the weak formulation and the Galerkin approximation problem have unique weak solution or unique solutions. Okay. Um, and that's just because um, we have coercivity and continuity of the bilinear form. How would I prove this? Well, I can either use Riesz representation theorem, very easy to do, because I have a symmetric bilinear form. Did I say that earlier as well? Yeah, I guess I should have. Right here, it's obviously symmetric, but the most important thing is that it's coercive and continuous. But that is a symmetric bilinear form. The fact that it's symmetric, coercive, and continuous means that this object is an inner product. And if we know that that's an inner product, then we can use the Riesz representation theorem immediately to show that the weak formulation and the Galerkin approximation are or have unique solutions. We could also use the Lax-Milgram lemma, but the Lax-Milgram lemma was built for more generic situations. Specifically, it was built for non-symmetric problems. The Riesz representation theorem takes care of the symmetric problems. Okay, but I've written here, we have a slight problem that I haven't really admitted to yet. And the problem is that we're asking for a finite dimensional subspace of H02. And these are hard to make. They're hard to build. Finite dimensional subspace of H01 were very easy to build. Piecewise polynomial spaces are easy to build in such that there are subspaces of H01. But in the case of H02 or H2, that's a problem because they're not easy to build. So let me show you why. So let tau H be a conforming triangulation of the polygonal domain omega in R2, for example. You can also do this in R3 and any dimension, really. Suppose that VH is a linear subspace of L2 with the following property, right? So far, it's a pretty rough space. L2 is not a space of smooth functions at all. But it's going to have a nice property. If I restrict V to any triangle in the mesh, then that's going to be a polynomial of degree at most R on K. So V restricted to any triangle is a polynomial of degree at most R on the triangle for every triangle in the mesh and for every V that I pull out of the subspace VH. Okay? Then what you can prove is in the proof you can find in this book by Bress is that VH is a proper finite dimensional subspace of HK if and only if VH is a proper subspace of CK minus 1 of the closure of omega. And these are the space of continuous functions of degree k minus 1. So that means if I want an HK function, I need this. So I already know that restricted to each triangle, I have a very nice function. In fact, it's a C infinity function. But globally, all that I know or I can know about that function is that it's HK if and only if VH is globally a CK minus 1 function over the closure of omega. Now, if this is true, then the dimension of VH is finite. If that's true, then we have a finite dimensional subspace, so that's good. But the problem is getting this to be true. Okay, that's the hard thing. So for the biharmonic problem, what do we need? We want this VH to be a subspace of H2, and therefore K has to be 2, so we need these functions to be globally C1. globally C1. Globally C0 functions are easy to build, such that they're polynomials on each triangle. But asking them to be C1 is a lot harder. So for the biharmonic problem, we need VH to be in H2 to remind you. And therefore, we need to require that VH is a proper subspace of C1 omega bar, globally C1 functions. So it turns out it's not it's not an easy task to construct piecewise polynomial space to satisfy this, but it is possible. And the technique I'm going to show you is the technique using what's called the Argyris triangle, the Argyris triangle. So an Argyris triangle, what we're looking at is a piecewise polynomial space where on each triangle, the polynomials are of degree 5. And what we're going to do is to build such spaces, we're going to have to make the functions agree at vertices, and not just the functions, but we have to make the function, its first derivatives and second derivatives agree at all the vertices. And we have to make the normal derivatives. This is what this indicates. The normal derivatives of these functions agree at all of the edge midpoint nodes. Okay? At all of the edge midpoint nodes. That's the only way that we can get a function or function space which is globally C1. So let's examine the number of degrees of freedom. What we're going to ask, or what we're going to look at here, are the derivatives at all of the vertices or the vertex nodes. So that means I from 1 to 3. All right. And we're going to make the derivatives, the 0th order derivative, which is just the function value, the first partial derivatives, that would be alpha, where the order of alpha is equal to 1. We're going to use those as degrees of freedom, and we're also going to use the second derivatives. So how many second partials are there at each vertex? Well, there's the second partial in x, second partial in y, and then there's the mixed partial derivative xy. All right, so that means we're going to make this happen at 3 nodes, so 3 vertex nodes for each triangle, and we need to match 1 derivative, or the function value, 2 first derivatives, and 3 second partial derivatives. So that gives a total number of degrees of freedom from using these degrees of freedom of 18. And we're going to use the normal derivatives at the edge midpoints. And so that's 3 more degrees of freedom for a total of 18 plus 3, or 21 degrees of freedom. So what we're going to have to do is, if we really want functions to be globally C1, then we're going to consider piecewise polynomials on this triangle K. And for near neighbors, we're going to make sure that the function values, the first partial derivatives and the second partials agree. So there's going to be a triangle over here, right? And we're going to make sure that the partial derivatives in the next triangle agree up to the second partials, and the normal derivatives agree. If we make that happen, then we know that the function is going to be globally C1, and on each triangle, it's going to be a polynomial of degree 5. And that is guaranteed to us by this next theorem. Let V be a polynomial of degree 5 on some triangle that is non-degenerate. That means it has finite area, okay? Positive area. Finite positive area, as usual. Then V is uniquely determined by the 21 degrees of freedom that I just listed. Those 18 degrees of freedom, function value, 2 derivatives, and 3 second partial derivatives at each one of the nodes, the vertex nodes, for 18 total, and then 3 normal derivatives at the midpoint, um, at the edge midpoint nodes. So 18 plus 21 or sorry, 18 plus 3 is 21 degrees of freedom. So if you tell me what um, the values of a polynomial of degree 5 are at these 20 degrees of freedom, then that uniquely determines that polynomial. Conversely, if I take um, information from a function and I specify it using these 21 degrees of freedom, then I can construct an interpolant that is a polynomial of degree 5. All right, so I'm not going to go into the details of this because even though I'm saying this, there's still a lot of complication that I'm sweeping under the rug. Right, but the Argyris triangle is the key to constructing a C1 finite element space. So let um, tau h be a family of shape-regular triangulations of the polygonal domain omega, and suppose that VH is this space. Okay, so we already said that this space is now possible, space which is globally C1 and piecewise polynomial of degree 5 on each triangle. And we're going to define an interpolant on that space now. Okay, so this interpolant is a lot harder to come by uh, than it is in the the usual Lagrange interpolating polynomial. So this interpolant, uh, we need a function to be globally C2 for this to work, and we're going to push it into this finite element space, VH. And the way we're going to do it is we're going to take a C2 function, C2 over omega bar, the closure of omega, and we're going to use the 18 degrees of freedom. So I'm going to put 18 DOFs at each one of the vertex nodes. And I'm going to use the 3 degrees of freedom at the edge midpoint nodes. Okay, the normal derivatives. And we just have to have the normal derivative of the polynomial interpolant, the piecewise polynomial interpolant, equaling the normal derivatives of v at each one of the edge midpoint nodes. And these partials, the zeroth order partial, first order partials, and the second order partials agreeing at every one of the vertex nodes. So what this does is it constructs a unique interpolating polynomial. It's not cheap to build. It's very expensive, but it is possible to build it, and it's going to be in this space. So this is a way of taking a polynomial or a function that's globally C2 and pushing it into this finite element space. So now, let's see, I've just got a page and a half, but I think, um, not even a page and a half. I think I'm not going to have enough time to do this justice because uh, it just requires a few more details. So what I think I will do is I'm going to push this topic to the next lecture and stop here. But what it is it's basically using all the pieces that we've used before. Say's lemma, we need an interpolation error estimate. We put those two things together and we get an error estimate for our problem. And like we did for the model problem in the order 2 model problem, we in the symmetric and the non-symmetric case, you can employ some sort of Nietzsche-like trick to get an L2 error estimate. So the first thing we'll do next time when we meet, which would be on Tuesday, is discuss this. Next Tuesday, we'll pick up here and we'll finish off this problem, this biharmonic. I was hoping to get it all done in one day. Didn't quite get there. Where are we going after this? After this, then we're going to talk about parabolic problems like the heat equation. And after that, we'll talk about a problem called the Stokes problem, and we're going to keep um, finding new and interesting problems that we can use our finite element approximations on. And so with that, I'll end the lecture.